Yeah, it should start recording. Okay, so let's start then. Yeah, so this is where we stopped last class. We discussed about the self attention. So first we discussed, of course, attention, and then self attention, which is sort of does not use a recurrent connection. So then we were telling that from self attention to how to go to transformers. That's the class of architecture that is sort of beating everything in both language and vision. But yeah, I mean, ConNets are also coming back, clubbing these two ideas. So ConNext, that paper was, I think, presented in one of the presentation sessions that sort of gave took best things from both of the worlds and prepared ConNext. But still it is a Con based architecture, but this one is there is no convolution involved. So let us see. So we actually talked about 4 problems. One is this positional encoding that addresses lack of sequence information because there is no recurrence. So and everything is processed parallelly, all the time steps. But it is important, at least for generation, that okay, which comes or which sentence comes where. I mean, we will have more concrete example, but at least having the position, I mean, the knowledge about the structure of the sentence, the position of the word, where does it appear, it should help. Multi-head attention allows querying multiple positions at each layer. So you saw that in simple self-attention or even attention architecture, that is attention with basic attention with recurrence. Where one key is or one position is emitting one query, and one position is emitting one key and key value pair. So from one query, you are sort of getting one maximum similarity, though it is softened, but anyway, it is sort of an approximation to the hard max. So you would like to query different for different purposes, different regions of the sentences you would like to get similarity from, so that it will enable us. We will see all these sort of examples, and that will be that will make things much more clear, but still sort of a high level idea I'm giving. And adding non-linearities, so there were no non-linearity per se to these VTs. So you are ultimately combining these values, and values are only linear functions of the activations, the hidden states, HTs, and they are linearly combined. These weights are non-linear, they are coming from using the softmax function, but ultimately this is linear, and that may limit the expressivity of the attention scores. And mass decoding is required for the generation, how to prevent attention lookups into the future, because attention just does not discriminate between past words or and future words. So it just attends everything equally. I mean, by equally, I mean it just queries everything equally. So, but to generate the next word in the sentence, it is useful to use what has been generated till now. Whether we are going to generate the verb, whether we are going to generate the article, maybe just a small example, a canonical example. That information, having that information or knowing that information would be good. So you need to have previous words to basically generate the future words, and the previous words depend on the future words. So this sort of circular dependency, how to basically mitigate that is given by this mask decoding. So let us go ahead one by one. So positional encoding. So what is the need for it first? So what we see when somebody says, okay, or the sentence says that the person ate a fish, okay. But what naive self-attention sees is just a bag of words. It's just a collection of words. 8%, wherever are the positions, where are the positions, that does not matter, because if you just switch alternate the positions, of these words, if you just think that, okay, the, ate, fish, a person, you give it to, as input to the self-attention block, it will give exactly the same output, okay, as the attentions, right? So, but that then basically does not have this information, like whether it's a valid sentence or not. So most alternative orderings are nonsense, but some change meaning. Suppose just these, the subject and object are replaced, so or changed. The fish ate a person, so that's sort of a basically meaning change. This is nonsensical. Say the 8% a fish, whatever, and this is again nonsensical. So whether you are giving sensical basically sentences, and whether it is I mean negative sentiment, positive sentiment, I mean things may change, I mean the meaning may change. So depending on the order, your classification of the, say, sentences sentiment will depend on. So we have to give the sentence or the word position. So in general, the position of the words in a sentence carries information, and that is very important to give. So small idea is that, okay, I mean, we were say remembering the self-attention, but we are giving these words one by one as input. But how about this, that add some information at the beginning? Beginning means at the, I mean, when you are passing the your words, because after passing the words you get the attentions, then you combine the values, and we have discussed last week that you can think it as a layer, right? So these output sort of combined values, output which are weighted combination of the values, these can again go in as a input to the next layer. So so what I mean by this at the beginning is when you are just giving these words as the input, that is in the very first layer, you just append, say, the position of the word. Say the first word is appended with 1, the second word is appended with 2, and so on. So those things you can do as basically position embedding. Now, there are many ways to do it, and there are two main ways, though, that basically dominates the scene. Two main ways to provide the model with this information. One is concatenating position embedding with word embedding. So whatever we were saying here, this T, that some way to convey to the model that this word's position is, say, first, this word's position is fifth in the sentence. So that way we are calling it as an embedding. So word embedding we have probably slightly talked earlier, but embedding you can think it as a mathematical representation. So word embedding we have definitely talked about one hot encoding, right? Or one hot embedding, sometimes people say. So one hot is that, okay, you have the representation is such that every word is a vector where the length of the vector is equal to the size of the vocabulary, and only one position in that vector is 1, which corresponds to the index of that word in the vocabulary, and everything else is 0. So that is just one sort of an word embedding. Others are there. For example, the continuous word embedding. We will discuss about how to get those word embeddings, etc., in the next week when we will discuss about some NLP applications. But for the purpose of this lecture, you can just think that word embeddings are basically, or embeddings are basically mathematical representations. So word embedding means mathematical representations of the word vector generally, and this position embedding is basically the mathematical representation of the position of the word. Okay, now so concatenating this position embedding with word embedding. So this is one option. Then another option is okay, so this one actually shows it. So okay, before I go there, so this is just the sentence, so the sentence translation tasks that we were our running example. So this was the French sentence, this was the first word, this was the second word, and this was the third word. So suppose these are the word embeddings, these numbers are the word embeddings corresponding to this word, and that word. Okay, this is suppose just 5 dimension for ease of visualization, I have just thought that, okay, this word embedding is 5 dimensional. You can think that the vocabulary, okay, it's not vocabulary length because all these are sort of continuous values. So, but think that it is a 5-dimensional vector that represents the words. Now you concatenate or append the position of the word. So this is P1, P2, P3. So position 1, position 2, position 3. It can be simply 1, 2, and 3. Okay. So this is now your basically the combined representation. So this is what I mean by this ht is f of this. Previously it was f of only xt. Now some word embedding is coming. Sorry, position embedding is coming. Now okay, so another option, so this was concatenating the position. Another way is adding. So adding basically means that, okay, if you have the word embedding as 5 dimension, you just figure out some way. So what are some ways that we will see? Figure out some ways to get the mathematical representation of the positions in a 5-dimensional vector. So it, for the first word, it will be P11, P12, P13, P14, P15. For the second word, okay, I think, yeah, there is a typo, just a copy paste error. So it will be, of course, P21. So this will be actually P21, P22, P23, P24, and P25. Yeah, I shall change these things. Yeah, there was one more correction that I needed to do earlier from last class, so I did not do it. But yeah, I will once do it and upload the updated slide. This slide is already there. Okay. Now this. Okay. So similarly, I mean, you understand. I mean, these are just the 5-dimensional position encoding. So this is so you get this as the one input which you will pass through this self-attention layer, and you will get the HTs. Okay, so that is sort of the or rather ATs. Finally, you will get the ATs. So these are the two ways. Now there is not a clear winner, as I mean I've seen this, that I mean there is not a clear winner, but both have as advantages or disadvantages. What are these? So both means this either concatenating or the addition. Just concatenating word position is simple and avoids messing up the semantic relationship between different words. So what does it mean? It will be much more clear next slide when I discuss about addition. But let me just try to give you a hint or overview that what is the role of the, or what should be the property of a word embedding. So if say king is one word and queen is another word, and say what is another thing, say something like caterpillar, whatever. So these two words mostly appear frequently in, say, a document, or they are very much related. But this, I mean, caterpillar with king or caterpillar with queen, they might not be very related, may not appear in many writings or documents where these words appear, that is king or queen appear. So your word embedding, that is the mathematical representation, should somehow capture these things, that okay, which words are similar, which words are not. That will help a lot of the down the line stuffs. Okay. So if this word embedding this in this 5-dimensional space, somewhere this king resides, and it should be, the queen should be very I mean some point very close to the king. Now when you add a 6th dimension, even if that position value is very high, suppose king appears in a sentence in 30th position, queen appears in 60th position, that very high value will reside on another dimension. So that's what I mean by this, that okay, it does not avoid messing up the semantic relationship between different words. That is, in that 5-dimensional space, subspace, you can say, the semantic relationship still exists. Maybe here it is distorted, but ultimately the network will figure out that whatever task it has to do, it will just look for this 5-dimensional space. And for the position information, if it has to do anything with the position information, it will take from this. So again, this is not very clear, I think, but you can ask if you have any questions. But it will be a little more clear when you see the addition example. So let me go ahead with this. So, this is the advantage, but the disadvantage is that it comes with additional memory and parameters. So the dimensions increase, as a result, memory increases, and everywhere, if you are using a lot of layers, that means everywhere the number of parameters also increase. Down the line, similarity computation between key and query may contain extra unrelevant terms. So ultimately, what you will use is this word embedding, or ultimately, I mean, this is say the word embedding. This will give you some key, again, some query you will get, and generally these dimensions are kept same. So when you multiply this dot product with this times this, basically k times q, you get one term, that is the scalar. But if it is like k plus k prime, that is this is basically the, not plus here means basically concatenation, and q plus q prime, or q comma, let's say, I mean, it's better this way, say key comma key prime, and this is scalar producted with, or dot producted with q comma q prime. You will have all these terms involving k into q prime, k prime into q, and so on, right? So these will basically be some irrelevant information that can basically bring down the performance generally, as I said, but there is not a clear winner. So people have tried these things, and probably the paper which we will be ultimately going into, the attention is all you need paper, which introduces the transformer architecture. They probably tried with say simple appending, and then tried with this addition, and they say that, see that, okay, things started to become slightly better in this addition philosophy, and then they tried to maybe justify. But there is not a clear winner. I mean, there are also learnable embeddings or position embeddings also. Anyway, so this I'm just giving very small overview. These are not that much required detail, but yeah, maybe just since this is not there in say many of the literature, I'm just trying to give you some idea. So this is this will give some irrelevant terms, which are, I am saying this. And you have some good, I mean, difference. So addition is another option that tends to work well, that will go. There are some links that I have given, provided, some blogs, some YouTube videos, which has some of these comparative analysis between addition and basically concatenation, and has some more detail on positional embedding and so on. So we will go into some more detail. Let me actually go to the next slide, and then we'll stop. I mean, complete this slide. So adding the word positions as all dimensions of position embedding. So addition is one option that we say. Now, what value can we add? So this is the word embedding, this is the position embedding, and position embedding has these 5 dimensions that you need to fill up. Of course, because the dimension of word embedding is 5. So what you can do is every element of this 5-dimensional positional embedding, you just give the position of the word. So un has this first position, shiot has this second position. So everywhere you give this 2, everywhere for this word you give this 3, and so on. So that is one option, definitely, right? However, adding word positions can significantly distort semantic positions of the words, especially for words in long sentences. That is what I was referring to when I said that, okay, we will go to the next slide and it will be much more clear. So this is, say, in some dimension, word embedding dimension, 5-dimensional space, say. This is queen and king, okay, the position of queen and king, they are very close. Now, as you add these values, if say queen appears, say, early in the sentence, and king appears, say, very late in the sentence of a long sentence, then what will happen is this, that ultimately this perturbation will be small and this perturbation will be high, because everywhere you are adding say 30, and here you are say adding 1. So this distance now has increased, which should be small. So the semantic relationship between these two words gets disturbed in this space. So that is a disadvantage. Then okay, let me actually stop here for questions. If you have anything, please ask. I have covered a bit of the things. Yeah. Yeah, Devojit, you have some question. Yeah.
Since we are unable to properly figure out what is a good method for concatenating embeddings, can we not create a neural network that can take this to and figure out the correct combination on its own?
Yes, that is done. And I think that is sort of the last sentence in this positional encoding slides. So maybe in 2-3 slides it will come. I mean, I'm not discussing it, but actually what they do is, suppose you have to learn, you decide that, okay, your word embedding is 5-dimensional. Generally, it is not so small dimensional, 128, 512, these are the dimensions that people choose. So suppose it is say D-dimensional. So you have to then get these D-dimensional positional embedding values. So you can actually learn a small, I mean, use a small neural network. From the input, it will just learn these D numbers. So that is always done. That can always be done. So learned embeddings are also done. And in vision transformer, actually, that is a difference. In this language transformer, that is actual transformer, not the BART or GPT that we will discuss next week. The classic transformer, they used some sort of a fixed encoding, which is dependent on the sine cosine. We will come to that. But for the vision transformer, they learned it. Okay. I hope this answers your question. If it is not, then yeah. Yeah, Rishabh, you have some questions?
Yes, sir. So like the follow up to the previous question, like that she Devjyoti asked that we can use neural networks for the same. So sir, the doubt is like we have a sentence, a cute puppy, and we have to generate a corresponding word embedding with the position intact with the embeddings. So sir, like how will we input will be the word embeddings for a cute puppy. So means how will we calculate the loss for that, sir?
No,
How
it will not be word embedding. I think I mean, I have not studied that learned embedding, but it will be the one hot encodings of those words. It will not be the word embeddings. Word embeddings will be I mean, the learned embedding, position embedding will be added to the word, if I'm not wrong.
So you meant to say finally we will get embedding after then using neural network.
Yes. Now finally you will get a position embedding, and then you will add. Then you will add with the word. Okay, that small neural network's task is to just get that word embedding. Position embedding. Okay. Okay. If there is not any other question, let me actually move ahead. And yeah. Okay. So okay, how about then adding fractions? Because we saw that just adding the positions can become prohibitively large. I mean, these positions values. So how about just adding fractions? So I think it needs to be a little zoomed out. So this zoomed in. So this is say 0th position. So what we do is that, okay, for 0th position, it will be basically, or rather, yeah, I mean 0th position and last position. Okay, yeah, 0th and last I'm just using. I think I have messed up a little bit with one and end, or 0 to n minus 1. But yeah, here I mean, you will get the idea. So 0th position is for that you will have the word embedding value 0, and the final position it will be 1. So how can you do it linearly increasing? So 0 into 1 over n minus 1, 1 into 1 over n minus 1, and 2 into 1 over n minus 1, or sort of n into n minus 1 into 1 over n minus 1. So this will be always 1, and this will be always 0, and this will be linearly changing. So that is one way, but you can definitively you probably be seeing the problem, that is, it is not great as the same position will have different encoding value. Suppose this acute puppy is seen, that is given, that is 2 more words are added, then these encodings will be changed. I mean, at least not for the this one, but this and this, right? Because this n value is dependent on the length of the sentence. So of course, that is not desirable, because position encoding should depend only on the position, not on the length of the sentence. So that is a disadvantage. So what about using a bounded function that extends till infinity? Because we need something which will work for any length of the sentence. So maybe a bounded function, because that is what we require. Unbounded will not help, because it will significantly distort the semantic meaning or semantic relationship between the words, because we are adding. So how about bounded function and extends till infinity? And maybe the first thing that comes to mind is, say, the sigmoid, and because that's sort of our good old friend. But here again, so this will be the position of the word, and this is the embedding values at each position. Okay. So what is the problem? The problem is that encoding. The problem is that the encoding very quickly saturates, and for all higher position values, they are same. So it very quickly saturates. After 3, I mean 4, 5, 6, 7, they are almost 1, equal to 1. So then this does not serve the purpose for I would say long sentences. For short sentences, maybe it can. Okay. So another one is this one, our again good old friend, say sinusoid or sine waves. What about a bounded but periodic function? And because why periodic? Because it extends till infinity. Okay. So it's bounded between 1 and -1. Now, if I use this, just I'm showing it for one time period for the time being. But still in one time period only, it has problem. Now, this x-axis is again word position, while y-axis is the value of the encoding, right? So the problem is actually different positions may have the same encoding. So just like here, it was having the same encoding for 4, 5, 6, 7, etc. Here also it will have, say, this position and this position, they will have the same value, right? And similarly others, many others. So this is again not an unique embedding choice. So what can be done? One thing is that we are when we are telling that this is the encoding value, or again encoding and embedding, I will be using intermittently, but yeah, it is basically the position embedding. This means that if you have your word embedding which is d-dimensional, in all the d positions for the position embedding, you will give this value. I mean, for this position, you will give this value. That's what I meant. But what you can do is, since you have these dimensions in hand, that you need to fill d dimensions, you can play with that. So you can use a cosine, say, for just the second dimension. Just say you can use a cosine with the same frequency. So this is the cosine wave, and now this position particularly has this value as the sine component, and say this value as the cos component. And what about this? This has the sine component same, but the cos component is this. So now they are not unique, at least I mean for at least this time period, right? So you can use sort of cleverly use the available dimensions to get these different embedding, I mean sort of unique embedding for different positions. Now, so what happens is that now you have 2 dimensions. So I think we were going ahead with 5 dimensions. So you can just copy these two, these here, and let's say the first one here. Okay. So that way you get a 5-dimensional position embedding also, and you can add with the word embedding. But again, there is a problem, because now this extends till infinity. So yeah, so this was the comment that the if 2 components of the encoding comes from 2 sinusoids, then problem is largely avoided, but not fully, because the same pattern repeats. So there is some point which is basically same as here, right? So this is or I think we were taking this point. So here, so these 2 positions will have same encoding, right? So again, the idea is then that you add one more sinusoid, some with different frequency. So that is the fix. So add more sinusoids with different frequency. So this is one, and so on. So you increase the frequency, and ultimately you can actually have you decrease the frequency, that is increase the time period, have a very almost non-changing sort of very slowly changing sinusoids also. So there are 5 basically sinusoids. So at each position you will have 5 values. So 1, 2, 3, 4, 5. And now if your word embedding has 5 dimensions, for each position you can get these values. So this is here, this will come here, and so on, right? Something like that it will go, right? So this way you take those many sinusoids, or sinusoids, or as many sinusoids as is the number of dimensions, or as the dimension of the word embedding. So this is sort of the idea that these people used in the paper. This is some math. Again, I will not go into much detail, but it's fairly simple. I mean, after you have got this idea. So this is d-dimensional. If the word embedding is d-dimensional, the PT, that is positional embedding for the tth position, when the word is at tth position, is also d-dimensional, and you have basically a sine cosine pair. So this is with some frequency omega 1, next pair is with some frequency omega 2, and so on. So you will have actually total d by 2 frequencies. Okay, and these are angular frequencies anyway. So if it is an odd number, so k say starts from 0, then PTI basically means the ith element of this vector. Okay, so first element of this vector is PT1, where k is 0. So that then only I becomes 1, right? So this is W or omega 1t. What is omega 1? This is 1 over 2 to the 0 by d. So 1 over 1. So basically omega k is omega 1 for that. This is 1, and so on. And you will see, so omega is this relation, right? 2 pi t, if I'm right. And this 2 pi I always forget. But at least omega is this, right? Now, this inter is inversely proportional to t. So if so basically this is what means is that as k's value increases, the value of k increases, this time period increases. Time period increases means basically the frequency is less and less, and so it's almost becomes a straight line at the end. Okay, so this is some values that they have chosen and played with, and so on. K varies from 0 to d by 2. Now, if we try to plot it again, we have to zoom maybe. So this is a 128 dimensional position embedding. So what I was telling as 5 dimensional, not that, say 128 dimension. If you try to plot these equations, and this is say the 0th position. The what is the positional position embedding for the word at position 0. This is at position 10, at 20, and so on. So this is 128 length, and this is 50 length. So for first 50 positions, it has been shown. And I mean, this is the color coding. This is 1, and this is -1, and so on. So you see that these latter parts, almost after say 70, the dimensions, these are not sort of very different for the different positions. So for all positions, for even 0 or even 10, etc., all these basically are same for these dimensions. The things are changing here. So this has some advantages. Again, I'm not going into much detail. I have probably spent I thought of that I'll spend probably 20 minutes on this position, but I probably spent a lot of the time. So when you basically add this thing to the word embedding, so word embedding actually does not, I mean, it learns to does not mess with this part, because this is where the positional embedding information is there. But it generally word embedding, the dimensions corresponding to these parts of the word embedding vector, they are generally learned to do the job. again, I mean, this is very high level. I think it is not possible to give you an idea about what I mean. And the paper only has like 5-6 sentences on position embedding. But still, I tried my best. If you have any questions, we can even visit those links. Even go to and come and send me the questions, because these are very much, again, there is no clear winner. These are very much questions of research. And this is the last bit that I was telling that comes as a response to this question. Learnable positional embedding is also sometimes used. Now, it sort of concludes the positional embedding discussion part. So if you have any quick question, please ask on this positional embedding. Otherwise, we'll go to the next parts. Yeah. Yeah.
Yeah, so just to confirm that this entire thing about the positional encoding, this is needed only in case of the the transformer mechanism, because if we have the the hidden layer, like the RNN connection from the hidden layer to hidden layer, then the positions are automatically deciphered. Is that correct interpretation?
Exactly, perfectly. That is right. Since we got rid of RNNs, sort of recurrent connections, we need to have some way to tell that, okay, this is the structure of the sentence. Otherwise, these are just isolated nodes of a graph, you can think. So that that will not be useful. So you can then tell that, okay, I mean, we'll see that when we decode it, then it still ultimately becomes a sequential process. But at least encoding part is faster. I mean, in encoding, you don't have to do the recurrence, because when you are, suppose it is a sentence translation task. So say from source language to target language. So when you are basically inferencing testing, that is when you have deployed this model. So you know that your source sentence is available at one go. So you have every word of the source sentence. But so there you just don't use the recurrent connections. But you also know that your generation should depend, that is the generation of the second word should depend on the first word, that is for the target sentence. The third word should depend on first two, that is first and second word, first generated word, second generated word. So you don't have any way to basically run parallelly, at least the decoder. So, but yeah, I mean, the attention mechanism is there, and transformer is not just attention, self attention. There are other attentions, cross attention, different other things that we will see by the end of today's lecture. We'll be able to see most of these. But what you said, your understanding is perfect. That if we are using recurrent connection, we don't need to use positional.
Okay, thank you, sir.
Okay, any other questions? Okay, if not, then let me go with this for the next one, that is the multi-head attention. So this says that allows querying multiple positions at each layer. Now, this very crudely you can think, you will see the parallel with the different channels in ConvNet. So in ConvNet filters have these output channels, right? So different filters, sort of the idea is that if one filter say learns the dog face, the other filter learns say the dog ear, say the other filter learns about say dog texture and so on. So this is very similar to that. I mean, a very crude similarity with this. But why do we need it first? So since we are relying on entirely on attention now, we might want to query to different time steps. So it is not that only one time step I am thinking that my next generation would depend mostly on. Okay. So what does it mean? Just one example. A sentence like the animal didn't cross the street because it was too tired. We would want to know the animal refers to it or it refers to the animal. If it is the animal who didn't cross, that is what is the subject to this verb? Street, animal, whatever. So so basically this animal would like to have relationship, know the relationships with cross as well as with it, right? So this will be just then allowed by this multi-head attention, and it is nothing. It's just the self attention that you have. You just do it for multiple. I mean, multiple times. By multiple times, we mean that for the same time step from where the query is coming, you generate one more query, and you generate one more key pair value from all the basically time steps with which the attention is required. So basically, if I draw it, so these are the time steps, right? 1, 2, 3 that we used earlier. So suppose you want to know that, okay, what is the relationship of this with this and both these. So what you do is your single head was just computing, okay, these dot products with it, and with it, using some W values. Say W1, I'm saying W and B basically, and W1, this again, I mean, I'm just avoiding this, giving this superscript, but some W values. And then you generate the basically queries by using this. So WQs, you can say, just I have to use. For this, you have this value and your key using some W K and WV. Similarly, this W K and WV, W K and WV for this time step. Now you compute this your cosine similarity, you pass it through the softmax, and then you linearly combine the values with these similarities, generated softmax similarities. You can do this thing with other WQs. So it is maybe WQ1, you can use say WQ2, WQ3, even WK1, so 2, 3, etc. And when you use WK2, WQ2, and say WV2, this will give your second head. You can do all the things very similar using just these key query and values, and but coming from the same time step. Okay, so it will be clear when I will be discussing it more. Here it is. It is there. I mean, just gave I just gave some word. Okay. So have multiple keys, queries, and values for every time step. What is this? So you have this x1, x2, x3, that is the input as earlier, h1, h2, h3, and we had this key query and value. So h1 gives this key one, q1, v1. But earlier we did not have this second subscript. Only one subscripts were there. K2, Q2, V2, and K3, Q3, V3. But now, since we have these subscripts, you may guess that we have other basically key query values. So you have other set of Ws, and that gives you the K1 to Q1 to V1 to K2 to Q2 to V2 to, and K3 to Q3 to V3 to. So you are using different sets of Ws here. You are using different sets of Ws here. By W, I mean WK, WQ, and WV, right? But all are getting it multiplied with, say, WH1 plus your B. So not only W, W and B. Similarly, say another head. Okay. So then you do this similarity computation, everything, dot product. Say I want to find the different queries for this time step. So you generate these queries, Q21, you basically do this cosine similarity multiplication with this key, and this key. Then do that softmaxing, then linearly combine with these three fields, right? These three values. But all are coming from this same H1, H2, and H3. You get this attention. Now it is called A21. So 2 is for the time step, and 1 is for the head number. Okay. Similarly, you get A22, where you all the computation is basically based on only this, the second row, and the third one. So compute weights independently. So these are independently. for each head, right? And this is basically the mathematically telling the same thing. So now it is not only QL and KT, but QLI, KTI, where I is the head number, and then there is ELTI, right? So L is the queries superscript, subscript, and T is the keys subscript. So T will vary for a particular L. So same thing. So T, as I said, T will vary, T prime. So you are doing the same thing. I'm not going into it. But here you are getting then alpha ALI, not AL. So for the ith head, you are getting the attention. Okay. Now, so you get three LIs. So I mean here AL1, AL2, AL3, or A21, A22, A23. I'm just giving this as an example. Why? How do you get the full attention or the final attention? It is just concatenating. So you concatenate these three. Okay. That is your output. Now, in this paper, the attention is all you need. You have around 8 heads per layer that tend to work well. So you have different layers. You saw self-attention layers. Now you have 8 heads. So now it is called multi-headed self-attention or multi-head self-attention. So sometimes you will find this term. You may say multi-head self-attention. Okay. So I mean, this multi-heading I have described. So if you have any questions, please ask. I think it is pretty similar, just or pretty simple, just that you have different heads. You just compute with different heads. Yeah. Okay. I think, yeah, Devajyoti, you have some question. Yeah.
Sir, we can say that the number of heads will tell us how many timestamps we are looking at, right?
No, it is not dependent on timestamp. So yeah, I have somehow taken both as 3, but you can have like the sentence as a 10 sentence long. Then it is not only x1, x2, x3, but it's x1, x2, x10. Okay, but the head can be 3. So for this, we are computing A2, 3, 2, 2, and 2, 1. We will compute A1, 3, 1, 2, and 1, 1. That is, this is the head number, head index, and this is the time index. So what will happen for the 10th word? A, 10, 3, 10, 2, and 10, 1, right? So this is for the 10th word, the third head given attention. This is 10th word, second head given attention, 10th word, first head given attention. Does it answer your question?
Yeah. Also, while calculating the key value, key query and value values, are we considering the same hidden state, or is the key of second head computed somehow from the key value of first head?
No, same hidden state. I think I have not given it here, but same hidden state. That is this QLI. If I write it, say the query, or let's say the key, KTI is actually WIHT plus BI. So first thing you remember, if you just forget about heads, what was one thing? That W's were shared, right, among these time steps. So W I am using for all the same T, all the T's I am using the same W. See, WI, I mean for the ith head, or let me just write the expression for the single head self-attention. So it will be KT W into, or WK into, I'm missing all these things because I mean K I used here. So okay, let me use K here. So K, okay, so KT was WKHT plus BK earlier. Now what you are doing is you are computing it for different heads. So what you will do, KTI, WKI, BKI. T is not changed. So the same HT, it goes to this key, the same HT goes to this key, and the same HT goes to this key, but with different weights. So this use, say, W K1, this use WK2, and this use WK3. Hopefully this answers your question.
Yes, sir, it does.
Okay. Yeah. I mean, I could have gone to that attention expressions also, possible, but I think I have written it. Yeah. So you have some questions? Yeah.
Sir, so this is basically kind of an ensemble.
Yes, but learnable, because ultimately you are concatenating.
Right.
Right. So yeah, of course. I mean, I think I find it most similar to, say, different channels of concat rather than ensemble. So, but that is also true. Different channels are also ensemble.
Yeah. Okay. Thank you, sir.
Okay, let me then go ahead with the next thing, which is adding non-linearities. This part is simple. Okay, so far for each successive layer is linear in previous one. So we have already discussed this. I mean, what is the problem? But let's see. So self-attention is linear. So this again, I mean, this is now the expressions that I was writing earlier. So KHT, now just think about self-attention. I mean, multi-head is a different component, and say this linearity introduction is different component. So again, just don't, just so that it is not clumsy, I'm with the notations. I mean, what I have to do, if I just try to do it for different heads, I have to add one I subscript. That I'm not doing. So, I mean, what you do for single head, in multi-head, you do the same thing with different weights and then ultimately concatenate. That's it. So, whatever we discuss it here in these two things, this and the next one, it will also be applicable to multiple heads. So, KHT is this WQ into HT, QHT is WQ into HT, and VHT is WV into HT. So, three different matrices. Then these are, I'm not even telling, but AL is alpha LT VT. So alpha L was that, alpha LT was that, VT was this. So I think I can replace it, and then since this is over T, WV comes out. So we make a nonlinear choice about the time steps. Why? Because this is nonlinear. This is giving me the choice that which one has most similarity, which time step has less similarity. We need to attend to, but that is, we make a nonlinear choice of the time steps we need to attend to, but we combine the, okay, this is not there, the linear transformations of those time steps. We combine, the linear transformations of these time steps. That is, this HT, this is only linearly transformed. So we combine only the linear transformations of HTs. Every self-attention layer is a linear transformation of the previous layer with nonlinear weights, because these are nonlinear weights. But ultimately, it's a linear combination of the previous activations. So in many situations, this may not be very expressive. So basically, you need to introduce some nonlinearity in the representation learning also. So it is very easy. I mean, you just add simple neural network with some nonlinear activation, nothing else. So this is what we had earlier, right? X, from there you have some H, and then why this is 1? This is just telling me that this is the layer number. This is not the head number. This is the layer. So we have many things here. So that's sort of why I will take as long as it takes. If you have time, we will go ahead at depth today. So it has layer, it has multiple heads, it has key query values and lots of things, right? And then in transformer, we will see encoder and decoder, both the things. Okay, so this is x1, x2, x3, this is H, these are key query values. Then self-attention, you do those soft maxing, or before that, say, cosine similarity computation or dot product computation, soft maxing. Then you get these attention values. So from x1, x2, x3, you get these A1, A2, A3. Now, these were linear, right? Till these, it was mostly linear, just the combination of the weights. The weights were, Kaushik, your question is right. Multiple heads, I'm not showing. I mean, these are two very different things. I hope this answers your question. If not, then you keep your hands raised. I will. Okay. So it is just a neural network at every position after self-attention layer. So this is what we added, right? This thing. Till this thing we were there. I mean, just single head self-attention. Now we have added this H12, okay, or H22 and H23, H32. So these are just, how do you get it? You multiply these A's with these W's and you add these bias. So it's just a small fully connected layer. But after that, you have one non-linearity, which is sigmoid, but generally people use ReLU or JLU, it is called GReLU. I forgot, but you have to use that JLU in your homework. I mean, it's just a single call of a function. So some learnable non-linear function, that is HTL, is just a linear layer followed by a non-linear activation function. It is just a neural network at every position after the self-attention layer. Okay, so these are all vectors, right? So element-wise, you multiply with this matrix and bias vector. That is not element-wise. Then whatever you get is a vector again, and that you element-wise pass it through the non-linearity. Okay, or non-linear activation function. Then you basically pass it to the next layer, self-attention layer. So referred, okay. So this is referred to as sometimes position-wise feed-forward network. You will see these terms sometimes, FFN. So as I said previously, it was MSA, multi-headed self-attention, and FFN is feed-forward network. But it is basically position-wise because for every position it is the independently computed. Now this I hope was clear. I mean, even in this portion there was any question, just let me know. Okay, then let us go to the last bit of it, that is masked decoding. So how to prevent attention lookups into the future. So what is the problem? Let us see. Nothing is preventing a crude self-attention language model to look into the future. So if you want to basically try to generate words, that is the task of the language model. It has that circular dependency, as I said. So before I go and show it, this is again, I think this is related to Kaushik's question in chat, that in reality we have many alternating self-attention layers and position-wise feed-forward layers, not just one. So we are just showing not all those heads, all those layers, etc. I'm just showing that, okay, I have got one output word, I am feeding it, I'm getting the next output. I am feeding this, I'm getting this output, and so on. So, and this is just one layer, but that is generally not the case. You have many alternating self-attention layers and position-wise feed-forward network. So just for illustration, I'm showing with one layer. Okay. So this is the figure that I have drawn earlier, that okay, this is fed in here, this is fed in here, the output. Now, self-attention at first time step needs to peek into activation at time step 2 and 3. So this self-attention, that is this query, will look into this key and this key to compute the similarity. That is what I have told in this first sentence. But activation at time step 2, that is this K2 and K3, or that depends on this activation at H2 and H3, that is time step 2 and 3. But this H2 and H3 depends on output from time step 1, and activation at time step 3 depends on output from time step 2. So this is where, you will not get this until you get these similarities of this Q1 with Q2 and Q3. And you will not get Q2 and Q3 until you get Y hat 2. So that is the sort of circular dependency, how to basically mitigate it. And it's an easy solution. You just don't look into the future. That's the thing it is saying. So easy solution is this, that previously it was ELT, is QL into KT dotted with KT for all L and all T. It's not the case for this solution, which is called mask decoding. So you mask out the future. So how do you do it? If L is greater than T, so if your query time step is greater than your basically key time steps, then only you have. That is, if your query is less, that is your query is looking into the future, then you replace this ELT, the similarity, with minus infinity. Why minus infinity? So that means you don't do these things. You replace this with minus infinity, because here your L is 1 and T is 2 and 3. So this condition satisfies, right? So why minus infinity? Because then the softmax for after softmaxing, that corresponding value will be 0, right? E to the power minus infinity. So basically now using or practically speaking, if you just try to inject anywhere this minus infinity or some positive infinity, this may jeopardize your code. So basically what you do is that you just replace this with 0 for L less than T inside the softmax. So you don't, I mean, even if you try to compute, maybe just you don't compute the ELTs, and instead you just you don't even compute the softmax for that. Everywhere you have these LTs where this condition is satisfied, that is L less than T, you just replace it with 0. Okay, so similarity is 0. So that is I mean the softmax. So that is the basically masked decoding part, and you can then do this generation. Now yeah, so this is the transformer slide that will start now, and this is sort of the peak that we will combine the pieces that we learned to get the classic transformer. But before I go there, just what we did learn here. These are the 4 things. But before that, again, I mean, attention, self-attention that we have learned earlier. But this today, what we learned today is positional encoding, multi-headed attention. Positional encoding is to give the positional information. Multi-headed is just the repeat of the single head self-attention with different weights. Just adding non-linearities. What it is telling is that after computing the attention, that is the weighted combination of the values, you just pass it through a linear layer and then pass it through a non-linearity, that is ReLU or sigmoid, anything. And then mask decoding, where it says that you don't basically compute the similarity if you are querying into future. Okay. So any questions before I go to sort of combining this in transformer? So, if not, then let me go ahead with it. So there are a number of model designs that use successive self-attention and position-wise nonlinear layers to process sequence. So successive self-attention, that is lots of layers, and then position-wise nonlinearity, that is to handle the nonlinearity. So basically, what the things that we learned to process sequence. These are generally called transformers. And why transformers? Because they transform one sequence into another at each layer. So if it is 3-length sequence, you are getting a 3-length sequence here, then again a 3-length sequence here and here and so on. That's why it is a transformer. This is the paper that basically came up with this idea, and they actually used it for language translation. The classic transformer, Vaswani et al., is a sequence-to-sequence model. It's a New Rips 2017 paper, a sequence-to-sequence model, and as I said, they tested it on language translation. But we will see later next week that it can be just only encoder using that. You can do classification or even other many tasks, pre-training tasks and so on. A number of well-known follow-up works also use transformers for language modeling, for BART, GPT, etc. We will at least brush through them a little bit next week. Okay. So let us go to the classic transformer. So as compared to a sequence-to-sequence RNN model. So I'll try to abstract out the idea of transformer here compared to a basic sequence-to-sequence model. Let me actually go ahead with this tab. I think Okay, so this is the basic RNN model where you had the recurrence connections. You have this source sequence, you have this and output this target sequence. Now, as compared, okay, so what do you have here in transformer? First is, of course, this the inputs x1, x2, x3, and then you have these basically the position in so you pass it through this. I mean, the position embedding we have seen discussed a lot, but then you get this added embedding, that is addition of position plus position embedding and the word embeddings. You pass it through self attention layer. Now you use this position wise nonlinear network, which we called FFN, right? So which is nothing. So from x1, x2, x3, you are getting say a1, a2, a3, and then you are passing them through or multiplying with a matrix and adding a vector, that is a linear layer, and you then passing it through a nonlinear activation function. So this is called this position wise nonlinear network, right? Now you basically repeat this thing n times. So this is the classic transformer. We'll come to the exact version that the paper used, and you repeat it for n layers. Okay. Now you have this decoder, that is this part. You have this position wise encoder again. I mean, though it is written encoder, I think it will be better to write decoder, but actually it is no, actually it is right. It is encoding this these positions and word 108 representations. So that's fine. But one thing is that you are using masked decoding here. Just remember that you are not using, though it is shown parallelly, you are not using them parallel. You are doing giving this y1 after this y1 hat is generated, y2 after y1 hat is generated, and so on. And similarly the positions also. Okay, so now again, this is, so that's why this is called masked self attention, not just self attention. Then you do this position wise nonlinear network. Here also you are doing this position wise nonlinear that is linear layer followed by a nonlinear activation function. Now this is basically something that comes, something subtle that comes. I mean, till this point, these seemed like very much these and these are very, very isolated. There is no connection from here. I mean, where are I mean, what are we generating? Okay, what are we generating? I mean, this is, I think I forgot to discuss. What are we generating in this encoder? From this x1, x2, x3, we are generating these key query values and then ultimately the attentions at the end, right? These attentions. But you are generating in between some key query values, 3 key query. If the sequence length is 3, then 3 key query values per head in each of the layer. 3 attentions per head in each of the layer, right? So similarly, at the end you will have these 3 key query values and 3 attentions. Okay, so where are we giving this? What is the y0? I mean, in sequence to sequence RNN model, y0 was very simple. I mean, you can just give the start token, and this end or the h at this end of this encoder would be the first initial h of this decoder. So where does this connection come? This is where actually it comes. It is the cross attention. So now don't be scared by this, the name cross attention. Cross attention is basically same as the classic attention that we discussed here. That is, when you are decoding, it is basically looking every time it is generating a word, it is looking at all the words in the encoder. So it is just that. So you are doing self attention here, masked self attention here, and here you are doing classical attention, which is called cross attention. Okay, we will also discuss about it, how does exactly it occurs in the next part. Okay, now again, since you are using attention, so after every attention, whether it is self attention or masked self attention or cross attention, you use a nonlinearity, because attention as such does not combine them. in nonlinear way. By them, I mean the input activations, the values. You do this position-wise nonlinear network, then you repeat it n times also. Generally, this n and this n are same, kept same. There are reasons for that also, basically for this cross attention. So this then you gives you the output, and finally, you can have one softmax layer, which will be just the classification layer. Okay, which will classify this one. So position-wise softmax. So if you have say this will just give the probability. Each of these will give the probability of each word in the vocabulary, and once this last end of sentence token is generated, you will basically stop. Because again, why I'm saying it will be generated, because it is masked decoding that is happening. One by one generation is happening. Okay. Okay. So before I go into cross attention, in this overview, if you have any questions, please ask. I mean, we might cover some of the things later, just the following subsequent parts. But still, if you have any questions, please ask. Yeah. Yeah, of course.
Yeah, sir. So I think you had also mentioned this previously, that in the decoder side, the positional parameters are not required, but
No.
they are still there. Can you?
No, it is required. It is required because the recurrent connection is not there. Okay, so you may think that once it is generated, since the recurrence is not there, I mean, it is still these connections are not there. Yeah. So you have to tell that this word, because once you are computing the attention, suppose you have generated 4 words. Okay, you are generating the 5th word. You are computing the similarity with each of these four words, each of the previous words. Now, if you jumble up them, these 4 words, suppose what was that? The dog did not, right? So this was the 4 word. Now, generation of this 5th word still tries to query these 4 words. Now, if you jumble them up, say the, did, not, dog, this will still be generating the same similarities. So to say that this structure is not right, this is the right structure, you still need the position. Am I clear?
Yes, yes, sir. Thank you.
Any other questions? Oh, let me go ahead then. So cross attention, a bit of discussion, though it is again, if you just put your classic attention head on, which we discussed for basically this model. So one thing is to discuss it. What I have told is, or again, sort of very similar sort of notation that I used in simple classic attention. H and S for encoder side hidden state, and S decoder side hidden state respectively. T for the time step here, capital L for the time step here, and because I was using small l earlier here, but the small l I am using for the layer number. So this is again, I'm just repeating. H and S, these are the same hidden states. I mean, not same, the hidden states coming from encoder and decoder respectively. L, that is small l, is layer number, and T is the time step. Capital L is also the time step, but for the first one is from encoder, second one is from decoder. Okay, now what do you do? So query output of position wise nonlinear network. So query you are getting from here. So because you are querying here, by here I mean decoder. So your cues are generated from here, keys are generated here. then you are querying with this queue, this case, that is the encoder case. That is the whole idea. So how do you mathematically express it? So you have to use this S, that is SL, capital L, and this you multiply with some learnable weights. This is your then QL, Q small l capital L, right? One important thing to note is that you are okay. That will come. So next slide it will come. Told it yet? Yeah. Here it is. So this is the key generation. So WKL. So this is some learnable weight, and HTL is basically the coming from encoder side, right? That was our notation. But note the L value; they are same. So cross attention. So if you have n layers in decoder, you will have n layers in n layers in encoder. You will have n layers in decoder also. I said it in a very loose term in earlier when I was giving the word. But this is how it is used. So if you are in the second decoder layer, you will use the hidden states from the second layer of the encoder to basically generate the key. So you are sort of querying the corresponding layer in the encoder side. So that is important. And value from the same HTL, I mean the same corresponding layers hidden state. Okay, and this is you generate for all T's in the decoder, and of course for all L's in the encoder. I'm just yeah. So T's are from encoder side, and small l is from decoder side. So all T's from the encoder side and all L from the decoder side. Okay. Now actually basically the same thing. That is, you generate the similarity for all these T's and capital L's. You generate the alphas, that is the softmax similarities. Then you combine these PLTs that you have computed here, right? So cross attention output. So this is C L capital L, I'm saying. Okay. Okay. In reality, cross attention is also multi-headed. So you don't have just WQL, you have say WQL I, right? This WKLI. Hopefully this is clear. So many superscripts, subscripts are there, but I think all the components we have discussed. So one by one you can try to add. So what are the attentions that we have seen? The self attention, the masked self attention, and cross attention. Okay, and all are multi-headed. Okay, one last detail. This is actually the last detail. I mean, we don't have much slides, but yeah, let's go ahead. So batch normalization is very helpful. What we have discussed way back, maybe 2 months back, but hard to use with sequence model. There are two reasons. Sequences are of different lengths, so makes normalizing across batch hard. So normalizing sort of requires you something in common. So if the lengths are not common, then it is pretty much hard. I mean, you just have to pad with all zeros. That makes things bad. And another thing is that sequences can be very long. So we sometimes have small batches, sometimes even one single example as a batch. So it does not make sense to compute mu or sigmas. Right, because statistics, I mean, it's a very small sample statistics, it will not work well. So the general wisdom is that we will try to, I mean, not try, we'll discuss what sort of way out we will use, but that way out is called a layer norm and or layer normalization. But people say that, okay, if you have ways or avenues to use batch norm, use that, don't use layer norm. Only if these cases happen that, okay, statistics is not properly represented. For example, the batch size is small, these have variable length inputs, etc., then you can go ahead with it. Anyway, so just okay, so the layer normalization like batch norm, but not across batch. So across what, that we will see. So this is the batch norm sort of recapitulation. So suppose we have d-dimensional vectors for each sample in batch. So this is the number of samples in batch B. You have some in some intermediate layer. These are the output vectors A1, A2 to AB. Then you might have forgotten, but that's what we did earlier in batch norm, that we compute the mu, that is mean of all these things. So if these are vectors, this is also a vector. We compute the sigma, which is like this. This is also a vector of sigmas. Then you have these learnable parameters gamma and beta, and you just learn this as the batch normed output, right? So ai minus mu over sigma. These are again element wise, right? So ai minus mu is anyway element wise, divided by sigma means basically you take the first element of this thing and divide by the first element of sigma, second, and so on. So this is still a vector. So that's what we get in batch norm. Okay. This layer norm does not have anything to do in particular with, say, a transformer. You can use it in other cases also, in coordinates also, or RNNs also. Okay. So it does. Okay. So layer norm, actually, I would have probably liked it as a something called a normalization layer, because, but probably that will be too generic. That's why they called it layer norm. But it basically means that it acts as a layer. That is, it is just, the output will just depend on the sample. So one sample you pass, you get one output. You pass 5 samples, you get 5 outputs, and so on. So it is not that in a batch you have 5 basically input. Ultimately in batch norm also you get 5, but the values will change whether you have the same 5 or say a 6th one, and so on. But if you have all the 5 or 6 for each one, always whether it comes together or not, this layer norm will be same. But yeah, this is again very hand wavy, but let's just see what happens in this layer. But at least just think that it is a layer. Okay, so one d-dimensional vector, not for each sample of the batch. Okay. And you are actually taking the mean of all the dimensions. So all the values, so for all the d values, you are taking the mean and you are getting a single scalar. Similarly for the sigma, and then the same formula, but remember that these are basically the same, the scalars. And but this is of course vector, this a. So ultimately you will get vector, but from all these dimensions, the same values will get subtracted. That subtracted value will be divided by the same sigma for all the values, and then gamma and beta will multiply. Okay. I have some question, I think, from Isha. Yeah.
So like the idea of the batch norm is to center the data around the mean and to make a uniform variance. So idea is to, so that we can convert faster. But then I don't find any intention behind using
this. Yeah, this is sort of a heuristic, but it also has similar, but it's not. It's like making it normalized with in the dimension. So again, I'm not going into the detail. If you are interested, you can go into the paper. But I have not gone into detail of it. Just how it happens, that's what I've told. But they might have given some intuition in the paper also.
So, sir, in this case, like if our attention is of d dimension, then the d represent the same, the dimension of our one attention output, right?
Yeah, it depends on where it is applied. But yeah, generally these dimensions are kept same throughout. So you can say that, yes. So let me quickly go through this. This was the one last detail. So now we are finally on the transformers, this famous image made famous by that paper. So I have taken this from the Sergey Levin slide. So I have given this credit, but actually it is, the image is from this paper. Attention is all. Okay, let us try to dissect this image one by one. So you have this input H bar T L minus 1 that you, when pass it through this multi-headed attention, you get AL. What is bar and so on, I'll come. But here what you do is you have the input, you have some input embedding. Now this input embedding basically is sometimes it is learned, or sometimes it is taken as standard, I would say, NLP embedding, some Globe embedding, and so on, BART embedding, etc., etc. But this we will cover more later. But just to give you an idea, this basically converts these one-hot representations to a continuous representation of the words. And you can think of it that, okay, you have some one-hot representation. If your vocabulary is say 10,000 words, then your one-hot representation of any word will be a 10,000 length vector. And suppose your word embedding space you want is 512. So you can learn a W which will multiply with this 10,000 length vector. So, and output a 512 length vector. So your W will be 512 times 10,000, right? So that you can learn here. So, but generally it has been seen that I mean the data is so less in case of say where you want to apply these transformers. Learning embedding does not basically help, because lots of parameters get introduced and you don't have so much data. So basically pre-trained ones are used, but you can use it. So okay, so you get this input embedding that is from word, some 512 dimensional word embedding. You add the positional embedding to this, and then this is what I am saying as, sorry, not output, the input. HTL-1 bar. Now, this particular is true. I mean, what I am telling that word embedding plus positional embedding, this is equal to HT bar 0, sort of. Okay. So only this, the first layer, this is true. Next, what is will be the HT bar L-1, we will see. But suppose in the first layer you get this HT bar 0, then your output will be ATL, which is just multi-head attention. Multi-head attention you now know. So you have ATLI for different heads, but ultimately you are concatenating, right? So you will be getting these multi-headed attention for each time step. Now, you go ahead, your next step. It is called add and norm in the paper. So we have taken the same image from the paper, right? What does it do? It essentially is a residual connection with a linear layer, or sorry, layer norm. So what does it do? It gets, you get the output earlier, this ATL, the concatenated multi-headed attention. You are adding this input. So from this input you itself got it, and that input also you are adding with the output. The idea is using residual, the sort of goodness of residual connections. So it has better gradient flow, and it models it the output as ultimately the addition or subtraction that needed to be performed. That is learned, the addition or subtraction part. So basically the goodness of, or the the goodness of residual connection they wanted to explore or exploit. So they do this residual connection, and then the layer normalization is used. Okay, so this is called the A bar LT. So remember, or see, this was ALT. Now this is A bar LT. Now what you do, you pass it through. Okay, let me go to the next slide. You pass it through this feed-forward network, the non-linearity. And what it is, I mean, what we have earlier seen, the non-linearity part was only this. Okay, so a linear layer followed by a non-linear activation function. What they are doing is, they are again, this output, they are again passing it through a linear layer. So linear layer, non-linearity, again linear layer. That is what they are calling HTL. Okay, so from H bar TL-1, you are getting ALT, then you are getting ALT bar or A bar LT, then HLT. Then you do the same thing with this input, that is residual connection followed by a layer norm. And that gives you the input, the output of this layer, that is the input to the next layer. So layer norm and this. Okay, so this input, from there you are getting this output, and so this input and that output they are both added and then passed through the layer norm. So this is now your HT or H bar LT, which again, I mean, this repeats n times. So then again, this output, this, and so on. Okay, this is what happens in the encoder side. So you get these n, I think this is written. You get these n layers. So in each layer, you get these key query values, right? That is what the encoder does. You just get these key query values. Okay, they use 6 layers with dimension 5 and 2. Actually, they had 2-3 versions of variations of it, probably. I don't remember exactly. Anyway, so now, okay, so this is the output. So multi-head attention keys and values. So each layer, you have this, for each time step, you have this for different heads. So L is the layer number, T is the time step, and this 1, 2 to M, these are the heads. Okay, so that you get. Okay, so this part, encoder part is complete. Now you do this part, that is, you have this output embedding. I mean, again, this is you are doing one at a time, sort of, because you are generating. So you need this positional encoding. That's we discussed. Why do you need positional encoding in generation? The whatever the output from the previous time step, you pass it through the embedding layer. Embedding layer, as I said, you can use a pre-trained embedding or learnable, but you add these two, that is positional embedding and word embedding, and this goes to your multi-headed attention block. Now it is masked. Okay. Same as encoder, only masked. Then residual connection with LN, basically this, then this, right? I mean, this was in encoder side. Okay. Now you have this, you pass it. Okay, let me go. So now you pass it to this multi-headed attention, but it is cross attention, right? So you have the key and value coming from encoder side, and the query is from this. So just notice this gap here, maybe. This will tell you that. And you get this multi-headed cross attention. So that then again, since you are having, every time you have compute attention, you do this non-linearity and residual connection, etc., etc. So basically the non-linearity and then the layer. So then again, you pass it through this one more feed forward. Sorry, this is okay, whatever I told. Non-linearity is here. It was just the residual connection followed by LN earlier. Okay. Now this non-linearity similar like this. So basically linear layer followed by activation function, then again a linear layer. That then again after that you do this residual connection and basically layer now. And then you do repeat it for in time steps, or sorry, in layers. And finally one linear layer, and you softmax over all the words of the vocabulary. Okay, so this is basically the sort of walkthrough of the classic transformer model. You have any questions? I mean, though we have sort of discussed all the parts in individuality earlier, but if you have any questions, please ask. Otherwise, I have 2 more slides to go over. Yeah, Rishabh.
There was small doubt, like when we are, we pass one input at a time, or we just pass one sentence at a time.
Sorry, your voice was not clear.
But we pass single input word at a time, or a complete sentence at a time.
Where in encoder or decoder?
So in encoder.
In
Encoder.
Encoder, you pass everything once, that is single parallel. In decoder, you pass it one at a time because you need the masked self-attention, right? That's what I say. That you for generating the second word, you need to rely on the first word. For generating the third word, you need to rely on the second word. That is the decoder. And who is generating? Decoder is generating. Encoder is not generating, right? Word.
But sir, like if I'm sending something in Japanese and I want it in English, so like I will send.
Your voice is very feeble.
Yeah. So sir, like I want some language translation from one language to other. So if I pass one sentence, like same, like a cute puppy, and I want it in Japanese, so I'll pass one complete sentence. But sir, the
See,
output.
when you are asking this question, specify me whether you are passing in to encoder or decoder,
Sir,
because things
initially
are very
it will be
different on encoder and decoder.
2 encoders, sir, and output is from a decoder. One
Output
language
is
from.
from decoder, yes.
So, sir, like I'm passing one sentence, and I would be needing complete translation at a time. So, but it will give one output, one word at a time, the decoder. So, how
Yeah.
will that work, sir?
Yeah, so that is what you get, right, in generation.
But I need a complete sentence at the output.
Yeah,
of
at the
decoder.
end, you remember the end of sentence token I have told earlier. So
Yes, sir.
you generate end of sentence and that generation is stopped.
So means means the output means the input will be fed and we'll waiting for the 3 cycles for our decoder to work. Like because decoder is giving one output at a time, one word at a time.
Please slow down because your voice is not clear, and so if you
Okay, so like what I'm saying is like I'm giving one sentence in English to encoder, and I want something in another language. So you said that the decoder will give one word at a time.
Yes.
So means for translating the 3-word sentence, I need to wait for 3. I need to wait for 3 cycles because
you may not need to wait for 3 times, because the 3-word sentence was in source language, it is 3 word.
Yes,
in target language, it may be 2, it may be 4, it may be 10. So whatever is the number of words in the target sentence, that many time steps you have to wait.
Okay, that was my question. Okay, got it.
Yeah. Okay. I think there is one more question. So yeah, Kaushik.
Yeah, so just to confirm, the difference between the HT and H-T is just the normalization. Layer normalization.
Yes, layer norm and the addition, that is the residual connection. So
and the residual connection.
yeah,
Okay.
because if you see just this, it will be clear. So it is HTL, it is H bar L, but it has this residual connection and addition.
Residual connection. Yes, sir. Sir, and for the masked multi-headed attention, I think you said it, but kind of confused between so many details. So the masked one was just preventing it from looking ahead. Is that right?
Yes. Masked multi-headed attention is yeah. So here, masked multi-headed attention, you are not basically, your queries are generated in previous times, but keys are not generated in future. So the words are generated here. Your for all of them, your keys will be generated in non-masked ones. In masked ones, you will not generate the keys here.
Right. Yeah. Thank you.
Yeah. Okay. Let me just go through to the last 2 slides. These are actually needed for the homework. I thought at 5 p.m. maybe it will be public, but maybe at 6. Just I'll need 1 hour. Okay. Yeah, this is the vision transformer. So it is not that only language can be used as transformer. So after NLP guys came up with this transformer architecture, so many efforts were given to use the transformer in vision, many other ways to combine coordinate vision, transformer, etc. But these guys in ICELA 2020, I think they Dosovitsky and all they basically successfully sort of engineered it, and it is pretty much data hungry. It's sort of not possible to do it in small scale. So what did they do is very simple change. So they basically patchified the image. So image is not a sequence, first of all. So how can you basically come up with a sequence out of a image? Is that you just patchify. So you just, the whole image, they divided it into 16 cross 16 number of patches, so 256 patches, and I think each one was also 16 cross 16 size, something like that. But anyway, so these many patches, then they fed it as a sequence. That's it. And one small thing, this will be more clear in BART, but this is another encoding. So these are the positional embedding, this 1, 2, etc. These things, that is like, this is 1, this is 2, this is 3, something like that. But this one is a special token that is all learned. That is, these images, they are passed through this, I mean, they are first vectorized, whatever were the number of pixels, I mean, height and width of these, they are just vectorized, and then they just passed through a linear layer. So what is meant by linear projection of flattened patch? It's just W, that is some weight times this vector plus B. Okay, so this is this linear projection, and they get this sort of equivalent of word embedding is this say image embedding. You can just think it is an image embedding, but it's not told image embedding, just the projections. Okay, projections of the image. Sorry. So now this is a special token. This actually is fully learned, and this does not go through linear projections. So this has this special position embedding as 0, and this is, I mean, suppose this output of this embedding, all these embeddings was 512. Suppose I think they use 796 for their smaller version, but whatever, just a say D dimension. So this is all the D numbers are actually learned. So this is all learned, these D numbers, and these just go through. So you have these 16 cross 16 patches, 256 patches, but actually your number of tokens are actually 256 plus 1. And this special one is learned. This is not coming from the image. This is just all these numbers are learned, and this actually goes to the classifier. So again, I'm keeping it a little vague at this point because you need to do the homework. So I would probably sort of expect that you will read the paper and then it classifies it. But I think everything else is covered. I mean, all these MLP, multi-detection, etc. And you will have the helper code, right? I mean, just like the homework one you had, you will have this helper code. And there, the position embedding is learned, but yeah, that is learned because it is a very less number of it. Anyway, so this is sort of the VIT, and they sort of at that time made the ConNet based architectures. There are 3 versions of it, variants of it. I think huge, large, and base, VIT base. So, but yeah, the trick is that they have to pre-train it on a lot of data. So that is one thing. And another thing is this one. This is small, like 2-3 lines code that you will be requiring to write. This is just a small part of this paper, this VIT for small size data sets. So since you have small size data sets and you are not getting the good results that is generally obtained for huge data sets using VIT, what this paper actually did, these authors, they actually use something called shifted patch tokenization. It's there is another thing that they did, but we are not including this as a part of the work. This is one, and it is nothing. It is just, you can think of it as an augmentation. So they are just shifting this image in 4 variants: left up, left down, right down, and now they are concatenating. So you are having then 5 versions of the same image. Then basically you are patchifying. So earlier you were patchifying 1 image, now you are patchifying 5 images, the same size images. Okay, nothing else. Then the same thing. Okay. So I have just given an overview of these 2 things because I will cover vision transformer in 2 classes from now. Just a few, I mean, in 1 hour, what can be covered, and then we will actually, we will have a guest lecture from, yeah, that I will announce maybe in next class on April 6th. That is the last class. So we will have 3 more classes, and then on 6th we will have a guest lecture. Okay, any questions? I mean, I have taken a lot of your time, but I thought giving this overview would be good. We also lost a few classes and the homework is there. Okay, any questions? A lot of material has been covered, so I will definitely upload this recording just now. No questions? Okay. In that case, I will basically stop this then. Okay. Okay, yeah, see you on Tuesday.